I do see a lot of new students here. This is great because I can see many of the UG1 students. The names are telling me that they are the UG first year students. I'm very glad that they are joining the 17th Alumni Lecture Series today. So let me just for the new people in the audience, let me just explain what this Alumni Lecture Series is. This is totally organized by our students in the Department of Physics. So this was, today actually the current PG2 batch, so they couldn't, many of them couldn't come because they are having their midterm exams. So Navanita and Ognivo are the main hosts, and then of course the entire PG batch, PG2 batch, they were. So what happened is that during the summer, from this July 2020, we just had some initial discussions about bringing in our recent alumni. Recent mean alumni of Presidency University. So these are our recent students who have graduated from our bachelor's and master's programs and are doing PhDs in different places, both in India and abroad. And since we are having a webinar, it got very easy because they don't have to travel. And so from different parts of the world, they could give the talk. And I can later share the page where we have this list of alumni lecture series. So initially we were having every week, and there were terrific set of talks. And then now, since we are having classes online and all that stuff, so we just got rid of this weekly schedule, and we are now running on a monthly schedule. So I'm very glad to let you know that, and I am today, since Navanita and Ognivo and some others from the PG2 batch are not present, so they have requested me to host the seminar today. And this is my great pleasure to introduce our student, our ex-student, former student, Alankar Dutta. So Alankar came to Presidency as an undergraduate student in 2014, and then he graduated in 2017, which was our bicentenary year. And then he got offers from many places, and then he joined IISc Bangalore for the IPhD program, the integrated PhD program. And Alankar's batch was one of the best batches we had in the last 5-6 years. And so Alankar was, when he was at Presidency, he was already interested in astrophysics and his greatest skill was computational skills. I mean, Alankar did amazing things in my classes, in other classes, with his amazing computational skills. And he was also interested in astrophysics. He did his BSc thesis on astrophysics, and it's my great pleasure to let you know that Alankar, for his PhD project, is now working on computational astrophysics with Professor Pratik Sharma. And he's going to tell us about the very exciting modeling of the circumgalactic medium. So Alankar, without further delay, please.
Thanks. So should I start my screen share then?
Yes, please.
Okay. So you can see it, right?
Yes, we all can see it.
Okay. Thanks a lot. It's been really a pleasure to come back to Presidency University, although virtually, and giving a talk here. And it reminds me of my undergrad days when I was at Presidency, and I feel very nostalgic and happy about it. So as the poster says, I work on the circumgalactic medium, and today I'll be talking some of the aspects of the circumgalactic medium, and through ways of doing how do we analyze circumgalactic medium by means of idealized simulations. So if you have seen the talk poster, then there it was like this spherical cow simulation. So it goes like this popular joke among the physicists that physicists often, in their attempt to understand very complex systems, simplify it down to unacceptable levels, like that of a cow being assumed to be spherical. But nevertheless, as centuries of work have proven, that this still seems to be kind of a good approach to understand an otherwise very complex and intractable systems. So fortunately or unfortunately, I also work on making such spherical cow assumptions of the CGM, which is the circumgalactic medium. And what is it? I'll talk about in some of the slides to come. So if one goes back in literature, the very first works on the circumgalactic medium was perhaps this work by Spitzer, who first seen that at high galactic latitudes, one sees quasar spectrum has some weird presence of cold gas. And it was hypothesized at that time that this cold gas is in rough pressure balance in the hot background medium. And this, at that point of time, people used to call the galactic corona, much like the solar corona outside the sun. And I was also very happy to see in the poster the image of the bullet cluster. I think it's a cigar, no, it's a cigar galaxy. And this is one of the motivations behind one of the models, which I will be talking about in the coming slides. So defining what's the circumgalactic medium? Well, circumgalactic medium is the gas which surrounds the disk of the galaxy, and it's within the virial radius of the galaxy, roughly speaking. And this gas is extremely low in density, so it's diffuse, and it's also multi-phase. Now, by multi-phase, I mean from a theorist's point of view that the gas which lives in a certainly in some confined spatial region spreads over a large range in temperature. And from an observer's point of view, again, the gas which comes from round about the same region has ionization potential of different ions spreading over a large values of ionization potential. And this is because of very low in density over a long period of time, was only observed in quasar in the absorption studies, like in the absorption spectrum. But recently emission spectrum also shows the amount of CGM, a large amount of CGM around the galactic disks. So summarizing, the CGM is like the so-called fuel tank of the galaxy, which feeds the galaxy with cold gas, resulting in star formation. It's also the waste bin of the galaxy, where the galaxy dump out gases from the galactic disk, come into the CGM, and also these gases sometimes rain back into the galactic disk in the so-called galactic fountains. So it's very important to understand the property and the evolution of the galaxies, that one understands what goes on in the circumgalactic medium. So here I'll not spend much time into this slide. So this is like some of the very broad questions in the in the field of this CGM studies, which will be important in the works in decades to come, I believe. So one is this: how do galaxies maintain long star formation history? If one sees that mass content in the galaxies and the star formation rate in the galaxies, so the time for which the galaxies are expected to form stars is much less compared to what is actually observed. So it must be that these galaxies then obtain mass from outside, and how does cold mass comes into the galaxies is an open question people talk about. Then this galaxy bimodality problem, where if you go from very high, low mass galaxies to very high mass galaxies, one sees a kind of a sharp dip in the star formation rates in the galaxies. And these are sometimes related to something called cold accretion in the galaxies, but again is a question which is important in understanding the aspects of galaxy formation. And then this famous problem of missing baryons, which is if you look at the stars and the ISM in the galaxy and count the amount of baryon in them, how that's done in observation is demands a specific talk in itself. So I won't delve into it, but assume that you know from observations that how much is the mass in the ISM and the stars. And then you see from the cosmic expectations that this mass in the stars is much less than what you would expect from the cosmic baryon fraction. And this is something which is important in a sense that what happens to these mass? Does it at all come into the circumgalactic medium, or is it just pushed out of the circumgalactic medium after it has initially come in? So this is like a study of the circumgalactic medium and its interaction with the outside regions. And then there's this metallicity. So you see that there is a significant difference in star formation rates in low mass and high mass galaxies. But if you move from low mass to high mass, the amount of metals that you see in the stars, ISM, and dust is almost flat. So what happens to you now? The star formation, as many of you would know, that produces metals by nuclear fusion. So what happens to these metals? Even you have large star formation, it's expected that you will see a lot of metals, but people don't see it. So this is the problem of missing metals, and this is specifically studying the interaction of the inner boundary of the CGM with the galactic disk. So regarding the idealized models then, I would say that in cosmological simulations, one could see it's excellent in terms of understanding the large-scale structure of the galaxies, what's their kinematics, how they are formed, and also in statistical properties of them. But still, they don't resolve a lot of important physics because of the because of the finite resolutions in them. And such physics is very important. And to understand those physics, one would need a very simplified model just focusing on those physics which these cosmological simulations don't account for. And these are important in understanding, having an understanding of the questions which I was previously talking about. Also, there is something called the infamous subgrid models in cosmological simulations. So these are like some, if you wish, recipes of how do you put in something which you don't accurately resolve and account for the physics in your simulations. And at the end of the day, these to get something out of cosmological simulations which makes sense with the observations, you need to tune these free parameters in your subgrid models. And this may turn out to be just some voodoo art of turning knobs and getting the right answer for all the wrong reasons. And hence one needs such idealized simulations to really have some physical motivations and better understanding in that regard. So how does one make observations in the circumgalactic medium? Well, I have talked a little bit about it before. So it's like you have a background quasar, and as the light travels through some region of gas in your circumgalactic medium, you have features in your quasar. And these features can tell you a lot about the physical conditions and the kinematics of the gas in your circumgalactic medium. Also, there is something called the down the barrel observation, which is you study the starlight coming from the galaxies, and there are features, or again absorption features on this starlight due to the presence of the circumgalactic medium. And this is a good way to see some galactocentric point of view of the circumgalactic medium itself. And then there's this detailed emission maps where you see the entire region around the galaxy. In case of absorptions, you just have at best, most of the times, one sight line per galaxy, and then you have many galaxies and you try to make a statistical study. But in emission map, you see the entire gas region around the galaxies. But these are very difficult, as I've said, because emission from a region scales as square of the density of the region. And because the circumgalactic medium is extremely low in density, you can have very less amount of a region that can be observed. So don't get scared by all these plots. All I wanted to say is that there are like many metals in the circumgalactic medium, and these metals are excellent traces in understanding, again, the physical conditions and the kinematic of the gas in the galaxies. So the plot on the right will show you what are the rough expected densities and temperatures to observe these metals. And on the left, you can see the plot which shows that these are the different metals which are moving quite fast, and these are having temperatures between 10 to the power 5 and 10 to the power 4 kelvins. So in the context of CGM, any gas which is around 10 to the power 4 Kelvin are referred to as cold gas, while within 10 to the power 5 are some warm mixed gas, and above that are hot gases in the CGM. And obviously in the CGM, you see a lot of forbidden transitions. Now, why that is so, I have some interesting animations behind for it, but I don't think that would be too much of a diversion here. So maybe I can skip that after the end of the talk. So moving on to what is the cloud crushing problem, which I have been working about for quite a while now. So as I've shown you that observations show very high velocity gas. So this is like there is cigar galaxy where you have small clumps of cold gas. And the idea is maybe these cold gas are accelerated in the outflows and you have fast moving cold gas. Similarly, if you look at, this is one of the Nature paper recently by Rukke, and it also shows of the Makhani galaxy, and there is this cold gas around this galaxy, and this cold gas also has very high velocities of thousands of kilometers per second. And similarly, in simulations, this is like an excellent volume rendering of a galaxy by Evan Schneider. And here also you can see there's this galactic disk and the gas coming out from the galactic disk, and there are like small clumps of cold gas in this disk. So zooming into it, one of such very small, somehow it's stuck, yeah. Zooming into this very small structures, what you can see is the cloud crushing problem, where I say that there is this cold blob and there's this hot wind coming in the background. And then do you ask that does this hot wind can transfer enough momentum and push the cold blob, and so that it can become co-moving in the hot wind? Turns out that there is a problem in it. So when does the hot wind can transfer enough momentum to the cold wind? Well, when the hot wind behind has swept up enough mass as that of the cold wind, and this gives a time scale, which is this drag time. And there is another time, competing time in this problem, which is this cloud crushing time. And this means that if you have some pressure perturbations at one end of the cloud, how long does it take for the pressure perturbations to travel to the other end and get the cloud destroyed? And as you can see here, that your cloud crushing time goes as the square root of chi, which is the density contrast between the cloud and the wind, while your drag time goes as chi. So your drag is much larger than your cloud crushing time. So before your cloud can become co-moving with the wind, it gets destroyed due to the turbulent mixing at the interfaces. So now how you can, this is what is referred to as the entrainment in problem. And now how you can rescue cold gases from getting destroyed is by radiative cooling. You can think of this radiative cooling as you have a cloud, and then it emits radiation and loses its internal energy, and hence its temperature decreases. So this is like a typical cooling curve, where you can see that 10 to the power 4 Kelvin is the cold gas and 10 to the power 6 Kelvin is the hot gas. And then you have an intermediate mixed gas at the interface of where you have turbulent shear in between your cold and hot gas. And this is the place where you have the highest cooling. And therefore, you have another time scale now in your problem, which is the cooling time. And if your cooling time in this mixed gas is much faster compared to the cloud crushing time, then you may destroy the cloud. You may have the cloud growing. And therefore, the thing now is that this can be translated into cloud sizes, and there is a threshold cloud size between which this works quote. So for example, this work by Gronke and O quotes threshold cloud size, and then another competing work like of Lee, Hopkins, and others also quote another threshold size. And now these are different by at most an order of magnitude, and even more than that as the relevant parameters of interest. So we try to analyze why this is happening, and then what is the then right cloud growth criteria. So our simulation is very simple. We have a cold cloud in a hot background wind, and this is what is the cooling term. These are the equations we solve, and this is the cooling term. And here you can see on the right hand side that we have the Mach number of the background wind and the density contrast. And you can see that these ratios are almost an order of magnitude, or perhaps even more than that, differing from each other. So we choose cloud sizes in between these two thresholds and see which threshold gives a better match. And we see that we are agreeing more on lines of Gronke and O than that of Lee et al. And now the question, okay, so these are like some of the density in our simulations, how the density changes. You can see that initially there is this destruction of the cloud, but the clouds again starts growing because we have very fast cooling in the medium. And now to see how we have how the thing mixes, we have some tracer particles which are like ink put in the cloud, and you see this also getting pretty mixed up. Okay, so we also just can show the shape of the cloud in 3D. So one can see how this cloud is in 3D. So this forms long filamentary structures with very spaghetti-like features on its top, and this has kind of like a fractal nature, which I am still investigating on. And we have some nice videos of these on our YouTube channel. If you are interested, you can have a look at that. Anyways, so these are again properties of the cloud. Each of these lines are each of the simulations, and you can see after the cloud gets destroyed, for initially there, if you are above some particular radius, your cloud mass grows over time. And now the reason for why these simulations were differing, and we were pretty perplexed in sense that we wanted to understand why these different simulations are giving different results. And we were really scratching our heads initially regarding the problem. And then once we got to know, pinpoint rather, what was really going on, we were as happy as this Mr. SpongeBob here. You can see that the cooling time of the hot phase goes as square root of square of chi, the density contrast, where your cloud crushing time goes as root under of chi. So if you have very high density contrast, then you have to run your simulations for a very long amount of time in terms of cloud crushing time, which these simulations don't. And because of this, they misidentify some of the clouds as destroyed clouds because their growth regime starts much later. So to have an understanding of this, that you need to run the simulations as long as you can, unless your hot gas starts cooling down. This is apparent in these simulations. For example, some of these clouds like this green and cyan cloud, you can see that if you run till 15 TCC, then you will wrongly conclude these to be decaying clouds, but in fact, these grow later on. So getting a bit more realistic in this sense that we are still working on this problem of putting in clouds in spherical outflows. And the way we do this is by means of some sort of anisotropic expansion, the way cosmologists do in a moving frame. And we solve the fluid equations and try to model the clouds in an expanding outflow, because that's the kind of systems we have in mind in these kinds of problems. I won't talk much on the mathematical details of it. And this is like the final problem which I'll talk about, the cooling flow model. Here you can see, perhaps this is the most simplest of all the models I'm talking about. So here you see a cold gas, and it loses its internal thermal energy due to cooling. As it loses the internal thermal energy, this is an ideal gas, so its pressure decreases, and as its pressure decreases, high pressure gas from outside comes down the gradient and creates a flow in the medium. So this is what is referred to as the cooling flow. So we draw simple spherically symmetric models of such cooling flows, and we also include a very simplistic treatment of magnetic fields in the simulations by just providing another fluid which is a pressure source for magnetic pressure. And we match our simulations with the results of the elasticity NG. Here you can see that our steady state solutions indeed are quite well in agreement with the time dependent solutions. And these are like several small clouds in the elasticity NG cosmological simulations of Dylan. And you can see that they are the small clumps, and we ask whether the fluid fields in these around these small clumps are comparable to cooling flows. And we see that some of the the average fluid fields around these clouds has a great resemblance to these cooling flows. So this shows that, again, that very simplistic modeling of idealized simulations can go a long way in explaining what are the bare minimum physics you would need to explain such complicated structures in general. So let's wrap up. So I have talked about the cloud crushing problem. Then I also talked about the cooling flows. And then I also talked about how they can be compared with cosmological simulations in general. So I think all of these problems can be put into a broad category of what are the different avenues by which you can form cold gas in the circumgalactic medium. Well, this idea is not genuinely originally mine, and I am very thankful to Mark Voigt in one of these ongoing KITP lectures where he had pointed this out. So you see that you try to start with so there are like two venues. One is this extremely cold gas, that is, you begin with very cold gas and you try to see whether it survives, or cold gas can come out due to condensation from the hot phases. But the thing which joins these two, I believe, is the turbulent mixing layers and thermal instabilities. And this is by some new recent papers also shed very much shed light into this. For example, I find the combustion studies where they study draw parallels between combustion of fuel in engines with this mixing in the cloud by Brent, and that really seems promising in this field. So I won't talk about this. These are like origins of wind in circumgalactic medium. So looking ahead, so I would like to conclude by saying that we are still working on this and trying to put in one by one different physics like thermal conduction, magnetic fields, and turbulence, and seeing individual effects of this and how these different effects couples with one another. We are also interested in producing synthetic observations, which are like creating synthetic emission maps or absorption spectra, and then we'll have a detailed modeling or a comparison with the observations. Obviously, this requires implementing chemical networks and assumptions about the physical state and kinematics in the ISM and the ionizations in the medium. Even our simple cooling flow problem has the potential of being utilized in some kind of these kinds of observational modeling. But yeah, so that's all. I would like to thank everyone, and I'm open to questions.
So thank you very much. Sorry.
I believe I haven't overshoot on time, did I?
No, can you hear me, Alankar?
Yes.
Yes. So thank you very much for the talk. Now, I think I do see, so this is the time for questions from the audience, and I do see SS raising his hand. So, Shomadip, please go ahead with your question. Please unmute yourself and go ahead with your question.
Well, Alankar, that's nice talk and nice work, I guess.
Thank you.
So, I don't know which one. I have a couple of questions. So, which one I should ask for? Let's see. So, you are only considering a thermal plasma, correct?
Right.
And you are doing a MHD simulation.
No, currently these simulations which I have shown has only hydro. We are putting in magnetic fields in an ongoing work which is going on. So these are like pure hydro simulations with radiative cooling.
Because since I am asking, because I know that this evaporation time scale which you are calculating, that highly depends on how the magnetic field also put pressure.
Yes. For example, there are some
etc. Everything depends on that.
Yeah. For example, there are some works by some groups like Christoph, who sees these clouds which are magnetically draped in your wind due to flux freezing, and these can protect the clouds and make your threshold cloud sizes go even have different values. And we are still looking into this problem and putting in magnetic fields and trying to find out how this cooling and mixing times change in case of magnetic fields. Even, for example, there are like small clumps in the cloud, and these clumps in presence of magnetic fields becomes more sort of filamentary structures. Yeah, magnetic field definitely introduces a lot of different problems to be concerned about.
And further is, what is the origin of these cold gas? Is it that your swept up material that's due to your instability, like relative instability they are growing in, and that's creating those kind of filamentary structure, or something different?
Yeah, so this is like one of the very challenging questions, and people have different models of saying how this cold gas arrives. So one is this, that you have some cold blobs which are pushed due to AGN activities or supernovae.
No, I understand those. In your simulation, what is the origin of this?
Okay, so in our simulations, it's like very idealized simulations, and we just put in a cold blob by hand and see, once the cold blob is there, does it survive? So our question is very simple. So we given a cold blob, does it survive or does it get destroyed? and what are the conditions of survival. But there is another point of looking how this cold gas comes in the first place. So there, I think things like precipitation and cooling time over free fall time. So there is this problem that if you have a cooling time and you have gravity in the background, and then there is this free fall time. So if you cool faster, then gas falls down, then you may have these small cold clumps. But yeah, this I think is a slightly different problem, but obviously these two are very much related.
Just a quick question. So you mentioned that time, how long you are going to run the simulation, depending on that whether it will show as the survival cloud or destroying cloud. What is the actual time scale you mentioned in terms of some collapse time scale? So what is that?
Yes. So it is of the depends upon what's the density contrast between your cloud and the background is. So for typical values like a density contrast of 100, so if you have your cloud to be 0.1 particles per centimeter cube, then you have 10 to the power minus 3. Given a density contrast of 100, then you have round about a few mega years of cloud crushing time, right? And it
Few
scales
mega years.
accordingly, a few mega years.
So roughly 10 to the power 7 to 10 to the power 8 years at least you have to run your simulation.
No, that is like one cloud crushing time. So to see growth, what you need to do
Growth, I am
is
saying it.
to see growth. Initially, all of your clouds will show destruction, but to see growth, what you need to do is you need to run several cloud crushing time. Now, how many cloud crushing time depends upon when does your hot gas cools. As long as your hot gas doesn't cool, you ideally run till that point of time. You cannot have this arbitrary thing saying most of the previous simulations did, right? We run till 10 cloud crushing time, and if we see growth, we'll see these clouds level as growing. If we don't see growth, we'll make this cloud destroy.
No,
We
but
say that
it cannot be arbitrarily large because you won't have the star formation to support the wind itself.
yes, yes, that's true. That's true. I was just talking about how in the context of just this problem itself. Now you have to see that once we know that this cloud is growing or getting destroyed, now how does this physically make sense? Now that is again a different issue in terms of what mega years do you see. For example, some of the clouds which we see are showing extremely late growth. They have very long cloud crushing time after which they show growth. So what happens in reality is they will never show growth, and these may be the origins of small tail-like structures, for example, in case of jellyfish galaxies, which are recently observed.
Okay, thank you.
Thank you, Shomadip and Alankar. So I see Rituban raising his hand for a question. Rituban, can you please go ahead and ask the question?
Yes. So Alankar, can you hear me?
Yes, yes.
Okay. So I was having some internet problems, so I may have missed this when you spoke. So what I have very naive questions actually. So what is the difference between the circumgalactic medium and the intergalactic medium? And
Okay.
what do you mean by multi-phase?
Okay. So the difference is a bit vague in a sense that there is no strict boundary between the circumgalactic medium and the intergalactic medium. So what people say is that the circumgalactic medium is a region, anything outside the disk of the galaxy and extending till the virial radius of the galaxy. But obviously, there is nothing to say that something drastically physically changes outside the virial radius, and anything outside the virial radius is collectively called the intergalactic medium, right? And
Okay.
does that answer the first part of the question?
I mean, in the sense that, so you are essentially saying that this is, when you are saying circumgalactic medium, you mean the intergalactic medium, which is within certain radius from the
Yes,
galaxy.
yes.
It's closer to the galaxy.
Yes, yes. So
And
it's like, roughly speaking, the kind of the region around the galaxies which has kind of thermally in thermal equilibrium with the galaxy itself, kind of virialized. So it's like within the virial radius of the galaxy. So it's kind of like a thermal equilibrium of gas.
but it's not really virialized.
Yes, yes, it's not really. It's just a matter of defining how much do you see as the circumgalactic medium, and what do you see at the intergalactic medium? But yes, this definition is kind of vague in terms of this is where your circumgalactic medium would end and this is where it would begin. There's nothing like that, obviously.
Okay, and what do you exactly mean by multi-phase?
Okay, so I think this is a very good question in a sense that so if you have different temperatures in your plasma, you will have different ionization states of the elements in your plasma. So theoretically, it means that you will have in the same region, if you have a wide range of temperatures of gas, then that would mean that you have different kinds of ionization states in your medium, and that is what people mean multi-phase. And as far as observation is concerned, if you see, for example, lines which are spanning over a large range of ionization parameters in your observation coming from roughly the same region, then you would say that this region is multi-phase. For example, here you can see like oxygen 6, which has like 10 to the power 5.5 Kelvin, and whereas other stuffs like let's see, silicon 3, silicon 4, which is very low, like 10 to the power 4, near to 10 to the power 4. So you have a very wide range of temperatures spreading in your
So
observation.
in that sense, would you say the interstellar medium is also multi-phase?
Yes, the interstellar medium is also multi-phase, but there are some subtleties in terms of the why or how those mediums become multi-phase compared to how these mediums become multi-phase. For example, in those mediums, you are mostly in this neutral regime, and there are like different dynamics in terms of photoionization and other stuff. Physical conditions may be different, but yes, they are also multi-phase.
Okay, thank you.
Thank you, Rituban. So any other questions from the students or anybody in the audience? Is there any other question? I do see a few of Alankar's classmates joining from different parts of the world. So is there any question from anyone? Okay, if not, then Alankar, I just have a simple question, and then I would request you to show the animation that you were talking.
Okay.
So a simple question is, can you go to the slide where we were talking about comparison with Illustris TNG?
Yes, sure. Yes.
Yes. So yeah. So can you just yes? I think this slide is this.
Mm-hmm.
Yeah. So my question is, what were you exactly comparing with the Illustris simulation? Sorry, I couldn't read the thing well, so and also a little bit missed on what you said. But so, what exactly did you take from their simulations and try to compare?
Okay. So what Dylan does in his simulations is he has this very he has an algorithm of identifying small clumps of cloud and knowing what are the centers and other stuffs in these small clouds clump of clouds, and then he draws profile of the field around these very small clumps. And what
Profile
you see,
of what? Density profile.
all the different profiles like pressure, density,
Pressure, temperature, density.
and then also you see that there are magnetic fields. So you have your two different kinds of pressure, like the gas pressure and the magnetic pressure, which and the ratio of these, which is, I think there is some kind of a beta parameter. Yeah, this is total pressure. Yeah. So these are like different fluid fields around each of these small clumps, and you have lots of clouds. So what you see here are the average profiles. And now what we see that whether these average profiles can be roughly explained by a simple cooling flow, that you have cooling in a region which is losing pressure and material is falling in a simple spherically symmetric cooling flow, which is very similar to how Bondi accretion takes place, except that it is due to cooling in the region. And then we also put in a magnetic field with an additional fluid component.
Okay, great. Thank you, Alankar. So my exact question is that what is the special? So if I look at Illustris, then what is this typical spatial scale of these clouds, and what are the resolutions and spatial scales in your simulation? Because
Okay.
that's a cosmological volume
Right,
simulation.
right. So these
So
are
what
like,
is the size of these clouds?
so these are like, as you can see, like cloud sizes of around a few kiloparsecs, like 2, 3, 4, 5, like few kiloparsec cloud sizes, right?
Okay.
And what our simulation is, our simulations are, I'll not call them really simulations. These are some simple steady state ODE solutions. So you can choose your ODE solver to have whatever radius you would like to go, right? And you have a few free parameters in your problem, which would we have something called a critical point, just similar to Bondi accretion. And then you just tune your free parameters, like what kind of values of temperature, pressure, and density would you like to have at your critical point. And you solve your ODE outside, and you solve your ODE inside the critical point, and see that whether such profiles are at least in rough agreement with these very complex cloud structures.
Yeah, but then do you have any scale, specific scale in your problem, like you
No,
define?
it is like a self-similar problem. So if you
Okay.
define some kind of a normalization and whatever you
Yeah. So
choose.
okay. So then you can of course like normalize your profile and compare with these average
Right.
profiles from
Right,
the
right.
TNG simulations.
Right, right.
But then Alankar, my question is that if the scales are, I understand that you are trying to see the shape of the profile and if it can explain the features that these guys see in TNG. But then my question is that, because I think from your talk we kind of understood that wouldn't the scales matter? Like if you are looking at kiloparsec scale, gas accretion and cooling, versus if it goes to, just parsec scale gas cooling, there must be difference. We know that there should be difference,
Yes.
because the density and the temperature profile is, I understand that you're talking about self-similarity, but wouldn't it matter? I would think that it would matter.
Yes, so this raises another, so this question, this is an, I think, excellent question. And this raises the thing that are cooling flows really approximations of what is rich physics? And is it that because these simulations do not go beyond, I think, a few kiloparsec scales, your resolution limited, then are
Yes.
cooling flows really approximations of these resolution limited thing, or is it something real? Is something which I think was raised in one of our discussions, and I am still looking into it.
Yeah, I mean, because you mentioned the subgrid physics. This
Yes,
is
yes.
that, like the subgrid guys, they would argue that if it's self-similar, it wouldn't matter that I don't
Right.
resolve the Bondi scale and just, extrapolate
Exactly.
something to 5 kiloparsec scale. But
Yeah.
this is, I think, going to sort of address this kinds of question, that what you see in smaller scales, is that really scalable to larger scales, and
Right.
with some factor or not. Okay. That's thank you so much, Alankar. Any
Just
other?
one thing, Alankar.
Yes, Shobhadip.
Sorry. When you are talking about cooling flow, that flow may not be through the outflows. That
Yes,
could
yes.
be
This is
from the where there is no outflow.
yes, yes.
Because
So
you are talking about the spherical outflow, then it is confusing.
yeah, so this is like a completely different problem compared to cloud crashing. You can think of these small clouds, which I sometimes think of as the tail of the cloud, which has already became co-moving in the hot wind. So you have no relative velocity between the wind, and then how you think of this, but still we see that these clouds are growing in mass. So is it just now it is in a regime
Yeah,
that,
I understand, but the cosmological cooling flow,
yes,
that's not through the
no, no,
hot.
no, 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 no. These are like very small clouds.
This
I'm not talking about these large cooling flows of
correct.
the IgM into the
Yes.
medium. So no, that is not what I'm talking about. These are like very local effects.
Any other questions? Okay, if not, can we see the animation, and then Shomendra, you can stop your recording after the animation. Okay.
Okay.
Alankar, can you show us the
Yes.
animation that you're talking about?
Sure, sure. So yeah. So why do we see forbidden lines in astrophysical systems? So I like to think of this like my school days. So suppose that these are me and my friends going to school, obviously we have to catch the school bus, right? So to catch the school bus, we how we say that these friends have either me or my friends reach the school bus at some point, like which I call tau call, and if they don't reach, then the bus waits for some point of time, tau ph, and then it just keeps. So imagine these thing as one electron, these one of my friends, and imagine this bus as some kind of an excited electron, right? And if you think of this as an interaction, then you have your and if you have your tau call, which is greater than tau ph, then you never reach the school bus, right? And your bus leaves, and the leaving of this bus indicates that you have a transition from higher state to the lower state, and it just leaves. And yeah, but if you when can you have your tau call which is greater than tau ph? When I think you are very far away, so you have very low in density, so you take very large amount of time to reach and hit the bus. So you don't have that mechanism of collision in your plasma, and when you don't have your collision, what happens is this bus can easily leave you behind and have emission coming out of the system. There's also another regime, like when your tau ph is very small. This happens for the normal emissions like the Lyman alpha and all those. In that cases, whatever your tau call may be, even if you have a dense medium like what we have in our lab, your bus always leaves, and then you always have emission coming out of your system. Yeah, I think that was it.
So you made this, and the whole animation was made by you?
Yes. I thought of this idea when I was reading about it, and yeah, so then I said, why not make a cool animation on it?
Okay, nice, very nice, Alankar. So then we can now probably, if there aren't any other questions from anyone, we can now stop the